Okay, so I am recording this video, and the purpose of this is to go over second order linear systems circuitry and explain how to come up with equations to describe their behavior. So I'm going to start with second order system that is a series system. This is the way the circuit will be laid out. We're going to begin with a voltage source, a voltage source here, which is, I'm going to label V sub S of T, and it's connected to an inductor, and then to a resistor, and then finally to a capacitor. And for now, we're just going to use letters to describe what they are, like this, okay? And the thinking here is that there is a current circulating clockwise in the circuit, I of T. This is called a second order system because it contains two elements that are storage elements, an inductor and a capacitor in this case. Okay, and then we're going to label these elements, the voltages across them. Since the current is flowing clockwise, it's going to be entering the positive terminal of each of these load elements as we mark them, V sub L, V sub R, and V sub C. And then using Kirchhoff's voltage law, we're going to go ahead and write an equation here to describe what's going on. So by Kirchhoff's voltage law, the sum of the voltages around a closed path has to be 0. We begin with a rise of Vs, and then we have a drop of VL, followed by a drop of VR, and then a drop of VC. Okay, so going around the loop, we come back to the place we started, and at the end of the path, we know that the voltages have to sum to be 0. So now what we'll do is rearrange this so that all of the elements that minus signs in front of them will be on the other side of the equation. So we have Vs is equal to VL plus VR plus VC. Okay. The current is the same in every element, and so we can rewrite this equation where each of these terms on the right side of the equation is expressed in terms of the current. Vs is equal to, okay, the voltage across an inductor with the current entering the positive terminal is L di dt. The voltage across the resistor, since the current again is entering the positive terminal, we can use Ohm's law and say that it's R times I. And then the voltage across the capacitor, we can express that as 1 over C times the integral from 0 to T of I. I'm going to use dt even though mathematically it's not quite proper, okay, because we have the limit here. The upper limit is t, and we're also integrating with respect to t. So we're supposed to use two different things here, but for now I'm just going to use them both because we really are integrating with respect to time. Okay, and it's not going to matter in another step anyway. So let's just go with this. And then added to that, we're going to put the voltage across the capacitor, initial voltage, because we're integrating from 0 to t, and we're saying, okay, we're going to include the voltage across the capacitor, and this is the expression here that gives the initial voltage across the capacitor. This is the expression that gives us the voltage across the capacitor in general. So now we see that all the terms on the right-hand side that have variables in them, right, they all have I. This is a constant over here. So we now have an integral differential equation, and we want to turn this into a purely differential equation, and we'll do that by taking the derivative of every term. So we start on the left side here, and we'll say we have d vs dt is equal to L d squared I dt squared plus R times di dt plus I. Okay, I. Since we're taking derivative with respect to t, that makes the integral go away. Okay, and then this here is a constant, so the last term is 0. The derivative of a constant is 0. And now we have a second order differential equation. It's called that because it has the highest derivative is the second derivative. And we have a first derivative. All of these terms are derivatives of I, and then we have I over here. Oh, well, I forgot to put in the 1 over c. That's got to be there too. Okay. And we don't know what Vs is. We just know it's some function of time. So we'll just say, fine, we'll take the derivative of with respect to t. Okay, so the next thing we're going to do is we're going to switch sides. We're going to take all these terms here that are on the right side and put them on the left side, and take this term that's on the left side and put it on the right side. So we'll take this stuff here and just rewrite it down here. We have L d squared I dt squared plus R di dt plus 1 over c times I is equal to dvs dt. Now, what we want to do is make it so that this expression is in the form where the first term, this second derivative, the highest derivative, has a coefficient of 1. So to get that, we're going to need to divide through by L. So that was going to give us d squared I dt squared plus R over L di dt plus 1 over LC times I is equal to 1 over L times dvs dt. All right, so we have a second order differential equation with constant coefficients, and you can see how the 3 components here that are load elements work into the equation, okay, and also how the source does. Now, this specific equation is written with the variable I, okay, but we could write equations for other second order RLC circuits that have V as the variable. Generally speaking, what we would like to do is talk about the second order differential equation in a more abstract way. And so what I'm going to do now is rewrite this equation in more general terms right underneath so that we can match things up, okay? Generally speaking, the second order differential equations that describe systems like this series RLC circuit can be written as follows. D squared x dt squared plus 2 times alpha dx dt plus omega 0 squared x is equal to f of t. Okay, and so f of t is the forcing function. And that corresponds in the equation above to this term. And you can see that this term is a scaled version of the derivative of the source. Okay, and so the only term that has anything to do with the source in this equation is on the right-hand side. That is the forcing function. It's based on what's driving the circuit, and it's of the form similar to, not exactly the same, but similar to what we are driving the circuit with. The other terms here, we have alpha here, okay? Alpha. Alpha is the damping coefficient. Okay, and this is a series RLC circuit. And for such a circuit, the damping coefficient is going to be R over 2L. It matches up nicely with what we have here, okay? Another term that we're going to include is the undamped resonant frequency, which is omega 0, undamped resonant frequency. Okay, and in this case, omega 0 is going to equal 1 over the square root of L times C. See, here is omega 0 right here. Okay, and we see that it's related. Omega 0 squared is related to this term up here. So we can match things up and get this figured out here. Now, the terms that we're using are related to mechanical systems. There are mechanical analogies to this. The circuit diagram is a schematic. It does describe an electric circuit, but these components can be used in lieu of mechanical components to describe a mechanical system as well, or any other second order linear system. Now, as was true before, when we want to solve such a system, we're going to find that our solution, which we'll use X here, okay, is going to have two parts. It's going to have a natural part and a forced part. Okay, so let me see. I think I'm going to write the forced part first. Let's write it like that. Okay. Now, the forced part is going to be, as was true for the first order systems, the forced part is going to be like the forcing function. So it's going to be of that same form. So we talked a little bit about what that means. So for example, if the forcing function, if what we wind up here on the right-hand side of the equation is constant, then we expect x sub f, the forced part of the response, or the forced part of the solution, to be constant as well. If the forcing function is a decaying exponential, then we expect the forced part of the solution to also be a decaying exponential of the same form with the same rate of decay. If it's a sinusoid, we expect the forced part to be a sinusoid as well. So that's how that goes. What I'd like to focus on, though, in doing this is the natural part of the solution. I guess I'll start off by saying the forced part. Before I go on to the natural part, I'll just say, okay, when we have the forced part, as was true for first order systems, the forced part on its own has to satisfy the equation. Okay, so for example, when we're looking for the forced part, then we know, looking back at this general equation here, we can write d squared x sub f dt squared plus 2 times alpha dx sub f dt plus omega 0 squared x sub f has to equal the forcing function. Okay, and once we propose some form of this, we should be able to solve for it from this equation. It has to satisfy this equation. But what we're going to do now is go on and talk about the natural part and how to get that. Okay, now I think what I'm going to do is, I do have some room on this page, so I think I'm going to work with it a little bit more here. What I'll do is I'm going to put a box around the equation that I'm referring to, which is this one here. The box around it, so that I'm highlighting it. Okay, that's the one I'm going to refer back to. And I'm going to put in some boundaries here so I can make it a little bit more clear what I'm doing. Let's see, like this. Okay, so I'm going to work over on this side of the page. All right. So in finding the natural part of the solution, I'll start up here. Okay, x natural. Okay. When we had in first order system, we found that x natural had to equal some constant e to the minus t over tau. Okay, and then what tau was, it could be either r times c, or it could be L over R, right? It depended on what kind of circuit we had. Now, when we have a second order system, the situation is more complex. As was true before, the natural part of the solution has to satisfy this equation, but we need to modify it first. Okay, so let's look at what x sub n needs to satisfy. Look back at this equation here that we have, and we're going to write d squared x sub n dt squared. Okay, so the first term is the same. We've put in x sub n here, and then we write the next term, plus 2 alpha dx sub n dt plus omega 0 squared x sub n, okay, is going to equal, not the forcing function, it's going to equal 0, okay? The idea here being that the natural part of the solution is what you get from the choice of components, how they're arranged, but it does not depend on what you're driving it with. So it's what you get without the source. obviously you have to have some energy stored in the circuit to be able to make this go, but it's the source-free solution, okay? Or the source-free part of the solution, the part of the solution that does not depend on the source, okay? The force part depends on the source. The natural part does not, okay? So this is what we have here. So when we have this equation here, this is what we got. And then we see, all right, we have an equation that equals 0, and it consists of some function that's scaled, right? Plus the derivative of that same function, also scaled, plus the second derivative of that function. And so what we get here is a function that when we take the derivative of it and then take the derivative of it again, and we scale these terms, when we add them up, we're going to get 0. So this means that we expect that when we take the derivative and then the second derivative again of the function, we're going to get very similar answers. We're going to get the function back again. Now that means that a good solution for this, x sub n, a good thing we can propose will be the exponential function. Okay, and this is something that we looked at before. Okay, it's a function of time, right? So it's going to have a t here, and it's going to have some coefficient that we don't know. Okay, we just figured something like that, and then the whole thing is probably scaled. And we think that's probably what it is. And this is what we proposed before when we were doing first order systems. And then we went in and found out particular things about it and found out that this form up here was what we actually got. Okay. Now for the second order system, we need to explore and say, okay, we're going to propose this as a solution and see how this goes. So in doing this, we're going to need to be able to substitute it into this equation. We're going to need to put x sub n here, the first derivative of x sub n here, and the second derivative here. So let's compute what they are first and then insert them into the equation. So the derivative of x sub n, dxn dt, is going to equal the function, again, e to the st times k, right? And then we need to take the derivative of the exponent with respect to t, and that's going to be s times s. So it's going to equal k s e to the st. That's it right there, okay? The second derivative, d squared x sub n dt squared, we're going to take this and take the derivative of it again, and we're going to get this expression, k s e to the st, and then again, we're going to need to take the derivative of this exponent here with respect to t, and that's also going to be s again. So this is going to be k s squared e to the st. All right, so now we have the second derivative, we have the first derivative, and we have the function, and we can put all three of these values into this equation here. So let's do it, okay? The first term, this one, okay? This one here, we're going to put in k s squared e to the st. That's the first term, okay? The next term, this one here, that's going to be 2 times alpha times the first derivative, k s e to the st. Okay? And then the third term is this one here. Okay? And that's just going to be omega 0 squared times the function k e to the st. Okay? And then we'll set this equal to 0. There we go. Right? Now looking at this, we see that every single term contains e to the st. So let's cancel that out. It's gone. Okay? Every single term contains k. We can cancel that out. K, k, k. And we're left with s squared plus 2 alpha s plus omega 0 squared, and that equals 0. Okay? Now, this equation is known as the characteristic equation. All right, and we can use this to help us determine what s is supposed to be in this proposed solution here. Okay, s is the exponent here, right? You can use it to help us figure it out. We see that S is a variable here. There's S squared, there's S again. And what we have here is a quadratic equation. And so we can use the quadratic formula to help us figure out what S is supposed to be. So if you recall the quadratic equation, it's based on this idea that you have AS squared plus BS plus C equals 0. And you can figure out what S is using the quadratic equation where S is equal to negative B plus or minus the square root of B squared minus 4AC all over 2A. Okay. All right. Now, having done that, we can go on from here and we can go ahead and solve this. So we can assign values. So A is equal to 1, right? Because the coefficient here is 1. B, this is B here, is equal to 2 alpha. And then C is equal to omega 0 squared. All right. So I'm going to switch papers now, and I'm going to just rewrite some of the stuff that I have here. Okay. As needed. So let's take this away. Down here. Okay, so what do we have? We're working with this equation now, right? We have the equation S squared plus 2 alpha S plus omega 0 squared is equal to 0. And we want to solve for S. So S is going to equal negative B, right? Remember, this is B here. B. A is 1, and this is C, okay? Negative B, so that's minus 2 alpha, plus or minus the square root of B squared. 2 alpha squared minus 4 times 1 times omega 0 squared, okay? And then we put in a dividing line like this, all over 2 times A, that's 1. Okay, so we can figure out what S is, right? S is going to be minus 2 alpha plus or minus the square root of 4 alpha squared minus 4 omega 0 squared, all divided by 2. Okay, next step. Minus 2 alpha plus or minus the square root of, all right, now here's the thing. Under the radical, we see that there is a common factor of 4. We can factor that out. We have 4 times alpha squared minus omega 0 squared. Okay, and this is all over 2. All right, and now we have a product here, the square root of 4 times the square root of alpha squared minus omega 0 squared. So we can rewrite this as minus 2 alpha plus or minus 2 times the square root of alpha squared minus omega 0 squared, all over 2. All right, and now, because we have a common factor of 2 in all terms, we can cancel it, leaving S equal to minus alpha plus or minus the square root of alpha squared minus omega 0 squared. So it looks like S has 2 possible values here, right? S could be minus alpha plus the square root of alpha squared minus omega 0 squared, or S could be minus alpha minus the square root of alpha squared minus omega 0 squared. Okay, those are the 2 things. So rather than having a single root, there are 2 possible roots here, 2 possible values, 2 possible exponential coefficients here for the natural part of the solution. So what they're going to be, though, is going to depend on what we get under this radical sign. Okay, so we need to consider the possible values that we're going to wind up with. So we're going to define the term that's known as the damping ratio. Okay, the damping ratio, we use the Greek letter zeta, okay, and we let it equal alpha over omega 0. And another way that we can think of that is, you know, well, it's basically, you know, the relationship between alpha and omega zero, right? And so there are a few different possibilities. We can consider them in turn. So I guess what I'll do now is I'll start up here, put a line here, and then I'm going to go up to the top here. We can slide this back down and look at it a bit if we need to. If the damping ratio is greater than 1, okay, so that was the case where zeta is greater than 1. Remember that zeta is equal to alpha over omega 0. So this is the same as saying that alpha is greater than omega 0, like that, okay? And that means the numerator is greater than the denominator. Now, if that's true, and we look at how we've expressed S here, if alpha is greater than omega 0, that means that the quantity under the radical is going to be positive, okay? So the square root of alpha squared minus omega 0 squared is greater than 0. Okay, so that means that we're going to get two real roots for S. There are two distinct real roots. Okay, and that means that we can express x sub n as some constant k1 e to the s1t, where s1 is one of the roots. Let's just go back here and let's let this one be s1 and this one be s2. Okay, here they are. They're different from each other. Okay. So we have one of them here, k1 e to the s1t. Okay, and then the other one is k2 e to the s2t. So we have two exponentials here that are going to have different exponents and probably different numbers here. Okay, k1 and k2 are not likely to be the same. All right. The other thing that we wanted to say is that S1 and S2 are both going to be negative. You see there's this minus sign in front of them. You can tell that whatever this value is here, it's going to be smaller than the absolute value of alpha. So we expect that both S1 and S2 will be less than 0. So that means that we expect these to both be decaying exponentials. This case, where we have this relationship with the between alpha and omega 0 and the two distinct real roots, this is called the overdamped case. That's case number 1. Okay, that's the first one. The next case that we'll consider will be what will happen when zeta is equal to 1. That is, alpha equals omega 0. Okay, so then we're going to go back and look at this equation that we have here for S, right? In fact, I should probably put a box around it. This is the one that we're looking at here. Okay. When we look at this, we see that if alpha and omega 0 are equal to each other, that means that the quantity under the radical sign is going to equal 0. So I can write that up here. Quantity under the radical sign, alpha squared minus omega 0 squared, will equal 0. There it is. It equals 0. So that means that this just goes away. Okay, and we're left with S is going to equal minus alpha. So let's say S1 equals minus alpha plus 0. And S2 equals minus alpha minus 0. So they equal each other. S1 equals S2, right? All right, now if we go ahead and we say that this implies that x sub n is equal to k1 e to the s1t plus k2 e to the s2t, just like we had before for the overdamped case. That seems fine until we say, well, wait a second, S1 and S2 equal each other, right? In fact, I'm just going to say that they're equal to S, right? This is just a single value. So that means that we can rewrite x sub n as k1 e to the st plus K2e to the st. And then we can further write this as K1 plus K2 e to the st. And what we have then is a single root, okay? I mean, what we have up here really is we have one real double root. You're supposed to have two because it's a second order system. But here it seems like we've reduced it to one, and that's not acceptable. We have to have two roots. We have to have two parts to the natural solution. And so we have to propose a different solution that will satisfy the differential equation that we're working from. I'll remind you what it is. Okay, the differential equation that x sub n has to satisfy is right here. Okay, it's the left-hand side of the equation set equal to 0. Okay, so whatever we propose has to satisfy that. So for this particular case, this isn't going to work. This isn't going to work. We need to have two roots to make it work properly and satisfy the equation. So we will use a different solution. We're going to say that x sub n is equal to K1 e to the st. Okay, but then we're going to include another term, K2 times t e to the st. Okay, so these are distinct. They both contribute to the natural solution. They both satisfy the equation. I am not going to go through and show you how that actually satisfies the equation. I'm not going to prove that this satisfies the equation. I'm going to state that it does. I'm going to assert that it does. So this is left. If you would like to derive that yourself or check it yourself, you're welcome to do so. But that we're just going to go with this. And this is the solution for the case number 2. I shouldn't have put a line here, but that's okay. Case number 2, where alpha and omega 0 are equal to each other. And we have one real double root as a result. This is the natural part of the solution. And this is called the critically damped case. That is case 2. All right. Now going on from there, we have the third case. The third case is the case where zeta is less than 1. Okay, and that means that alpha is less than omega 0. Okay, and that also means that this radical, okay, in the expression for S, which we have over here, this radical, it turns out that the quantity under the radical, alpha squared minus omega 0 squared, is going to be less than 0, right? This piece here. Actually, I probably shouldn't have the radical sign here at all. Sorry about that. Yeah, that's kind of unclear. I should just put it like that. Okay, anyway, so this quantity under the radical is going to be less than 0, and that's a problem because we're not supposed to take the square root of a negative number. If we do, we're going to get an imaginary number here, right? So what we're going to wind up with is as follows. We're going to have S is equal to minus alpha plus or minus the square root of alpha squared minus omega 0 squared. Okay, that's what we get. And this here is a real number. Okay, it's negative, which is fine. And then this here, because what's under the radical is negative, this is going to be an imaginary number. So what we end up with are two roots. We have a piece that in each of them that's real and a piece that's imaginary. Okay, and that means that we're going to wind up with two distinct complex roots. Okay, they are two distinct complex roots. They're complex because they have, each of them has a real part and an imaginary part. And you see that this sign is going to be negative, right? So just keep that in mind when we talk about what the solution looks like. The solution for this has a specific form. X sub n of t is going to equal K1 times e to the minus alpha t. Okay, so there's that real part. right? Times the cosine of omega sub n of t. And I haven't defined yet what omega sub n is, but I will in a minute, okay? And then here we have k sub 2 e to the minus alpha t sine omega sub nt. And omega sub n equals the square root of omega 0 squared minus alpha squared. So notice that it's the terms that we have under the radical, right, except reversed. So it's the negative of them. And in this case, that means this is going to be a positive number. Okay, omega sub n is positive. All right, so this is what we get. And then I want to talk about what this is. The two distinct complex roots, this case is known as the underdamped case. So I want to talk a little bit about what these functions actually look like. It really depends on what you have as the constants here in these cases, right? But I want to just talk about them in very general terms. So the overdamped case, when we look at the natural part of the solution, that's what I'm referring to right now, just the natural part. Okay? Natural part of the solution, since it's two decaying exponentials, and we expect something like this. I'll write this overdamped case. We have x sub n is equal to k1e to the s1t plus k2e to the s2t, and both s1 is less than 0 and s2 is less than 0. Okay, so what do these look like? Well, the first term, I'm just going to assume that k1 is positive. Okay, what's it going to look like? Something like this. Here's k1. We're only worrying about t greater than 0 here. I should put this in t. Okay, and what does k2 look like? I mean, the other term is going to look, I don't know, it depends. I mean, the decay is different for these, but here's k2. It's got a different sort of, value of the coefficient of t, right? So it's going to be decaying at a different rate. And then we add them together, right? And then the sum is going to be a decaying exponential. Sum, decaying exponential function. Okay. And as I say, that's just an example. It could be that K1 or K2 or both are negative, in which case the way that they're combined will be a little bit different, but generally speaking, this is what we expect. Something like that. Some of those, okay? Now, when we have the critically damped case, we have x sub n is equal to k1 e to the st plus k2 times t e to the st, and s is going to be negative again. So that means the first term is going to be a decaying exponential. Okay. And I'm just going to draw something in like this. Okay. So here's K1, and I'm making up, its decay. It's just some value here. Okay. And then the other term, we have this situation where we know that at 0, t equals 0, it's going to be 0 because t is 0, right there. It's a factor, right? And then after that, as t increases, this factor will, of course, get bigger, but then e to the st is going to get smaller because s is negative, right? So it's going to look something like this, maybe, but it's going to go down like that. Okay, so when you add these together, right, you're going to get something that will be non-zero at t equals 0, and then it's probably going to rise a bit, but then drop down and decay and die out. It's a transient response, as these natural responses are in all these cases. Okay, now the last case, sorry, I got a little box here. Okay, the last case, the underdamped case. Okay, we have this, and recall that x sub n is equal to k 1 e to the minus alpha t times cosine omega sub n of t plus k2 e to the minus alpha t times sine omega sub nt. Okay, now when we have a situation like this where we have a cosine and a sine, both of them have the same frequency, and they're both multiplied by some constant here with e to the minus alpha t, we can rewrite this as the square root of k1 squared plus k2 squared, okay? Cosine, I'm sorry, e to the minus alpha t, I forgot about that, e to the minus alpha t, that's a term, okay? And then cosine omega sub nt minus a phase angle, okay? I will not discuss the details of how we get the phase angle, but just some phase angle, okay? The phase angle basically has to do with K1 and K2, okay? But I'll just say it's a phase angle. It's a shifted version, so, okay, because that detail doesn't matter right now. I just want you to know that you're going to get a sinusoid, okay, that's got this exponential term in it, just like these did up here. Okay, so what do we have here? We have a constant out front, constant, and then we have a decaying exponential function, and then we have a sinusoid here that's shifted, okay, shifted in time. So the way that we graph this is we use this exponential term here, and that is going to be the envelope for the function. I'll put this in down here. All right, so now we see that we have a decaying exponential, and then we have a mirror of it here, and this envelope is symmetric about the horizontal axis. Now this is going to act as the envelope for this cosine function. Okay, now notice it's shifted, right? So we don't know what the phase angle is, so we'll just put something in here. It's going to look like this. It's going to decay and go down to nothing like that. Okay, so we assume that this just keeps going here. Draw it out a little bit more. So this is what you have. You have this rippling that occurs, and the amplitude just keeps getting smaller and smaller, but it will continue to oscillate around the horizontal axis until it just peters out into nothing. And so that's how each of these cases is. You have a natural response that is going to decay and go down to nothing. Okay, in these two cases, I didn't add them together. I just showed the two pieces that would be added together. Here, same thing here, but here I took the two pieces and I combined them in this expression so that I could draw it a little bit more readily. So the idea is that when you have these different cases, what's happening? Well, I just want to mention one more thing, and that is what we would call the step response. So with a step response, the idea would be that you would have this situation where what you're trying to do is basically flip something on, okay? And you'd say, all right, in order for my system to go from not working to working, ideally what I'd like it to do is as follows. I'd like it to be off until I get to a certain point. Say it's like this. Okay, it's off, and then I want it to suddenly jump up and be on. Okay, this is the step up. Okay, so off, then on. Okay, now realistically, when you have a system, the response to the system is not going to be instantaneous. Okay, but you can, depending on how you arrange your system, and again, it could be an electrical system, it could be a mechanical system, you could have a response that is pretty close to this, depending on how you choose the components, how you put it together. If you have something that is overdamped, then what that implies is you're going to have a response. It'll start here, okay, but then it's going to be rather sluggish. It will eventually reach the target, but it takes a little bit of time to do it. So that's overdamped, okay? Then you could have underdamped. The underdamped case is where you respond, but you kind of overshoot, and then you oscillate, and then eventually you settle down after a few ripples and you get to where you're supposed to be. Okay, so you may get to the target faster, but you overshoot it. Okay, and then you go kind of back and forth and back and forth, and then you finally settle down to what you're supposed to do. So there's a quicker response, but the overshooting. Okay, and then critically damped is kind of like the Goldilocks, just right, you know. You just go up here and you get something that's more like this. Okay, it's very hard to hit that critically damped case. Okay, and you know, maybe you want it doesn't go up. It's not going to go up immediately at the target time, right? It's going to also need a little bit of time, but it probably isn't going to overshoot, right? It's going to go up to where it's supposed to go. It takes a little bit more time. So there are trade-offs involved in these responses. When you design a system, you're going to maybe you have to ensure that it doesn't overshoot, whatever the system is. Okay. And you say, okay, well, in that case, to really make sure that it doesn't overshoot, I better make it overdamped. Or maybe you need a quick response time, in which case you're going to let it overshoot, and that's okay. So having it go up like this is fine, right? Because you need it. Speed is the thing that matters. And if you overshoot, it's okay. You'll settle down and get into the steady state that you need over here. Okay. And then, or maybe critically damped, depending on how you do the design. Okay. And so, as I say, this can be true for lots of different kinds of systems, not just electrical systems. So this is as far as we're going to go with this right now. And hopefully there'll be more coming soon.